In previous videos, we delved more deeply into the different types of information that's available at each step of a sequential multiple regression analysis. In this video, we'll go through this one more time, kind of more quickly now, just hitting some of the highlights that we've covered in previous videos, but also pointing out how one might report the results at each step of the process. Okay, let's go. Now, to begin, I think it's always a good idea to literally map out the model that you have in mind for your analysis. You may not include this in a write-up unless you're going to go on to do a path analysis, but literally drawing it out can help confirm your understanding of the design and help to ensure that you enter the variables in the correct order that you intended to. Now, when it comes to summarizing the results, people will often focus on the coefficients table, typically including a table just like this, although you may see people dropping some of the columns. For example, you may notice that researchers may not include the 95% confidence intervals in their coefficient table. They may not even report it in the text. Researchers typically don't include the zero-order correlations in the coefficient table. Remember, those are just the Pearson product moment correlations of each predictor with the outcome. But they may report those in a separate correlations table, of course. Also, as we previously noted, I think we typically don't include the partial correlations. Now, when reading articles, you may see the semi-partials included in the coefficients table, but I think you probably see this more often reported as either a squared semi-partial or the change in R squared at each step, either in a coefficients table or just described in the text itself. All right? So how would we summarize the analysis that we've completed in our previous videos? Well, researchers will often summarize the results model by model by model, starting with model 1. Now, when interpreting the results, remember that all of the effects in model 1 are just different ways of describing the total effect of mother's education, right? Now, I think it's good to start off with the unstandardized regression coefficient, RB, along with the t-test and p-values so that you can note whether or not the effect is statistically significant. I mean, here we see that that is the case. It is statistically significant. You should then interpret what that effect means. Something like in model 1, a 1-unit increase in mother's education was related to a 0.131 increase in grades. You may also report the standardized coefficient, beta, or you may see some report beta instead of the unstandardized coefficient. Now, remember, it's the same t-test, so if you've reported the t and the p for the unstandardized coefficient, you don't need to repeat them if you're also reporting the standardized beta. But you may also want to interpret the standardized beta. In this case, it's telling you that a 1 standard deviation increase in mother's education is associated with a 0.357 standard deviation increase in grades based on model 1. Now, as I noted, some will include the confidence interval in the coefficient table. Common notation for reporting a 95% confidence interval is to place the values in brackets with the upper and lower limits for that confidence interval inside brackets separated by a comma, right? So other times, though, people may just report the 95% confidence interval narratively in the text, or they may put it in brackets following the test statistical results, their t and p value, all right? Now, if you describe this in the text, you might write this out as something like, in model 1, the 95% confidence interval for the effect of mother's education was 0.097 to 0.165, or put that in brackets and package it with the t-test and the p-value. Again, you see it all sorts of different ways, right? But let's take a step back for a moment and do a little refresher on this, kind of just to prime ourselves again. And remember that that 95% confidence interval, again, is that the range of values where we think the true population value lies, right? Consequently, if the 95% confidence interval overlaps the value that we expect to see if the null is true, with regression coefficients, that's 0. We expect it to be 0 if the null is true. Then again, if the 95% confidence interval overlaps 0 in this case, we know that we won't reject the null hypothesis with a p less than 0.05. I mean, how can you reject the idea that the population value is 0 if 0 is in the confidence interval where you expect to see the population value, right? Now, in this case, our 95% confidence interval does not include 0. So we know we'll reject the null hypothesis if alpha is 0.05, right? If I'm confident that the population value is somewhere in that range, right? And 0, the null value, is not in that range, how can I think 0 is a plausible value, right? We know we'll reject the null. Okay, well, enough of that little review. Let's keep going. Now, like I said, researchers may or may not report the confidence intervals for regression coefficients, but I personally think you should. It provides a nice sense of how precise that point estimate of b equals 0.131 really is. Do you think the true population value for the total effect of mother's education is really close to 0.31, or could it be anywhere in some broad range of possible values? And then there's the squared semi-partial correlation. So I noted a paper may include this in the coefficient table, but you may also just see it reported in the narrative text itself. In this case, squaring the 0.357 gives us 0.128 using non-rounded values. Now, instead of the squared semi-partial, you'll also often see researchers report the same idea using the change in r squared at each step. In this case, notice that because we've added a single variable, the change in r squared and the squared semi-partial are the same thing. So they have the same value, right? But if we'd added 2 or more variables in a step, they wouldn't be the same thing, because the change in variance due to a group of variables will be different than the unique effect of individual variables in that group, right? So that's model 1. Now, when reporting the second step of a sequential multiple regression, model 2, the focus is then on the variable that we've added in that step, school quality. Remember again, this is the total effect for school quality, right? It's the total effect because we're controlling for mother's education. We're removing that part of the school quality effect that was related to or driven by mother's education based on our model. So here you'd now want to report the same information for the total effect of school quality in model 2. Report the unstandardized regression coefficient along with the t-score, the degrees of freedom, the p-value, right? Depending on the data, you may also want to include the standardized coefficient. And again, I recommend including the 95% confidence interval either in the table or directly in the text using that bracket notation. I'll report it both ways, kind of depending on the paper. Plus, again, I would recommend including the squared semi-partial or the change in r squared. And again, because we've added a single variable, the change in r squared and the squared semi-partial are the same thing, so they have the same value. Now, either way, this tells us that school quality increases the r squared by 0.014 and uniquely accounts for an additional 1.4% of the variance in grades beyond or controlling for mother's education. This 1.4% of the variance in grades, again, is after we've given mother's education credit for any variance that school quality and mother's education share. So that's how you might summarize the Model 2 in a write-up, right? But notice I haven't talked about the effect for mother's education in Model 2. Well, you can report the same information for the effect of mother's education. It would be different in Model 2, right? Model 1, it was the total effect for mother's education. Now it's the effect for mother's education controlling for school quality. Now, while in class we may exactly do that very thing and interpret every variable in every step, in practice, researchers often don't re-examine the effect of variables that were previously entered and discussed until the final step of the analysis. So let's move on to the third step of our sequential multiple regression and start by focusing on the variable we entered in Model 3, study hours. Like mom's education and school quality in the earlier steps, this is the total effect for study hours. It's the study hours effect controlling for mother's education and school quality, right? Now, based on our model, any effect that study hours shares with mother's education and school quality goes to those variables that we've already covered in the previous steps, right? So, working off of Model 3, we report the same information for the total effect of study hours. The unstandardized coefficient, maybe the standardized beta, the squared semi-partial, or the change in R squared, and the 95% confidence interval. Now, notice what we've done. We've cumulatively focused on the total effect of each predictor based on what we think their causal sequential effects are on subsequent predictors in the outcome. One way of thinking of this is that we've divided or partitioned that total R squared, the total effect of all of the predictors as a set, into pieces associated with each individual predictor. For clarity, let's take a moment and look at a Venn diagram here. Now, while you wouldn't generally include a Venn diagram in a paper, it does clearly show how we really are dividing all of the total R squared into the pieces related to each individual predictor based on their causal or sequential series of effects. This is what we've been doing so far in this video. But as we know, the effect of some predictors may overlap with each other, so to fully understand and appreciate the impact of our set of predictors, it's often valuable to also look at the unique effect of each variable, that variance in the outcome or effect that's only related to that specific predictor, right? Now, as we previously saw, these are the unique effects of each variable controlling for the effects of all of the other predictors in the final model, Model 3. In terms of unique variances, these are the squared semi-partials for each variable in Model 3. But again, remember the unstandardized coefficient and the standardized coefficient in Model 3 are also the unique effect of each variable, just expressed as raw units or standard deviations, respectively. So for the final model, and in addition to reporting the results for the new variable that we added in this step, study hours in this case, researchers often report the same information for all the variables in the final model as well. The unstandardized coefficient, maybe the standardized beta, maybe the squared semi-partial, and the 95% confidence interval again. Now, think about the difference between the earlier steps in which we added these variables, mom's education and school quality, versus this where we're looking at them now in the final model. When we described mother's education in Model 1 and school quality in Model 2, we were describing their total effects. But the final model describes the unique effect, or their direct effect controlling for all of the other variables in the model. Because of that, you may want to contrast the total versus the direct or unique effect of those earlier variables, particularly if there's a large difference in the direct effect versus the total effect. For example, if the direct effect is a lot smaller than the total effect, it suggests that the indirect effect a variable has on the outcome through other variables in our model, the effect or variance it shares with those other predictors, may be relatively large, right? On the other hand, if there's little difference between the total effect and that direct unique effect, it suggests any indirects are probably relatively small. It would look like the variables impacting the outcome in ways that are unrelated to the other variables in our model. Now, we'll get into this later, again, with path analysis. I can't wait. But for now, it's great if you just have a sense of why this might be true, even if you're not calculating those indirect effects yet. Now, because this is our final model, you should also typically report the total R squared for the model from the model summary table for the overall model at that point. Now, of course, we previously summarized the cumulative increase in the R squared as each variable was added to the model, and we just described the unique effect of each variable in the final model. But report the total R squared as well, just to be clear on the overall effect of the predictors as a set or as a group, okay? And likewise, if you're doing that, be certain to report the f-test for the total R squared from the ANOVA table. Again, just to be clear whether or not that total R squared is statistically significant. Now, I guess I should note, you can of course report the total R squared and the overall F when summarizing each of the individual steps along the way. There's nothing wrong with doing so, but you definitely want to include them at the end of the final model, all right? Now, before wrapping up, I do feel I have to point out that these examples reflect standard types of patterns that you will typically see nearly all the time when performing multiple regression analyses. But there's always a but. Strange things can happen.
I've seen things you people wouldn't believe.
There are fascinating things that can happen. Not just weird data quirks, but real things in the world around us that can lead to results, total effects, unique effects, direct effects, indirect effects, that appear paradoxical, maybe even impossible. Fortunately, those types of situations are probably relatively rare, but I've seen them confuse even excellent researchers who look at their analysis and are like, what? Okay, now we'll talk about some of those, but that's for another day. All right? With this, we'll wrap up our series on sequential multiple regression and the good, the bad, and the ugly as well. It's been a wild ride. All right? Bye for now.